Stop. Okay, so it's looking like I don't know how the quality is, right? Okay, there it is. Now it's getting good. Sorry for being a little bit late. I was having some technical difficulties, but I think we have fixed it. So this is going to be a lecture on kind of the basics of circuits. So we're just going to go through the three major parts of circuits. We're going to go through voltage, current, and then resistance. And I sent out a PDF of the notes that I'm going to go over to you guys on Remind. And I'm also going to attach that once I upload this video to the event for this video as well. All right, so let's go ahead and get started. Okay, so all circuits, in order to work, need three things. Okay, we need voltage, which is the energy source for the circuit. Okay, we need a current, okay, which is something that carries the energy. All right, and then lastly, we need some type of resistance, okay, and that's what's going to use the energy in the circuit. So those are kind of the three basic things that all circuits need to work. We need a voltage, we need current, we need resistance. Now, could you technically build a circuit without resistance? Yes, you would just likely end up setting things on fire, and normally we like to avoid fire. That being said, I know that that's not always the case. Fire can be fun. Okay. So let's first talk about voltage, which is our kind of energy source in a circuit. Okay. Now, examples of voltages or energy sources are, of course, going to be the battery, or like a wall socket, or what's sometimes referred to as a cell. Okay, and we represent these voltages or energy sources in a circuit with two lines. Okay, one represents a positive terminal, the longer one represents positive terminal, and the other represents negative. Or sometimes we might see it drawn as this. This single one is a battery, or a cell rather. This is a cell and this is a battery. Batteries are usually many cells, and it's a good chance I messed that up. But they are interchangeable. And the long side is the positive side. The short side is the negative side. Okay. So like I said, voltage is the energy source, but we can actually define it as the amount of energy per charge. That's how we can think about it. So what each charge is actually carrying. And we can calculate the voltage by using the equation V equals W over Q, where this V right here is the voltage in volts, okay, which is represented with a V. And this is also sometimes called potential, like potential energy difference. Okay, so potential difference and voltage, if you see them written, are the same thing, and that's measured in volts. This W over here represents energy, okay, and that's going to be in joules, okay, with the letter J. And this Q here, which you might recognize from some stuff that we've already done, is the charge, and that's in coulombs, okay, which is represented with the letter C. Or there's our Greek letter ohm, or omega, which is called an ohm. So we throw a pair of sunglasses on it, and now it's a coulomb. You guys didn't think just because we were distance learning I was gonna, you know, like stop with the corny jokes. No, always gotta include those. So that's a coulomb. Right, this is cool. There. And if you have questions, you can of course ask them in the Q&A section. Okay, so that's our equation for voltage. Now, we won't really need to use that equation, but I think it helps in the definition of what voltage actually is. So 1 volt actually represents 1 joule of energy for 1 coulomb of charge. And if you're wondering like 1 coulomb is in terms of like, I don't know how many electrons it is, 1 coulomb is 6.25 times 10 to the 18 electrons. So a whole heck of a lot of charges is in 1 coulomb of charge. Okay, so in a 9-volt battery, each coulomb of charge has 9 joules of energy, and so on and so forth. So our 120-volt wall sockets have 120 volts of energy per charge coming at them. Okay, so in any circuit, this voltage, which remember is really just a measure of energy, must be conserved. Okay, just like energy in like a car going down a hill has to be conserved. So this should say in any circuit. Okay, the voltage or the energy must be conserved. So what does that mean? The voltage exiting the battery must get completely used. And we're getting used by the resistors, so it must be completely used in the circuit. Okay, so this is considered Kirchhoff's loop rule. That in any loop that you make in a circuit, you have to conserve energy and therefore use up all of the voltage within that loop. Okay, it's just a different form of energy conservation for circuits. Okay, but if you see something mentioned Kirchhoff's loop rule, this is what it's referencing. Okay, last thing we're going to talk about with voltage is how we measure voltage. It'd be great if I could spell. Measure voltage. Okay, so we measure voltage with something called a voltmeter, right? Meter because it's a measuring device and we're measuring volts, so voltmeter. Very easy. In a circuit, that's represented with a circle with the letter V. And these get placed around or bridging, if you want to think about it, bridging the element they are measuring. Okay. And the reason why we have to bridge the element is because voltmeters measure the amount of voltage or energy used up in that element. So we need to know the amount of energy coming into the element and the amount of energy coming out of the element. So if I had a battery here, let's say this is a 9-volt battery, okay, and I want to place my voltmeter right like that. Now, in reality, voltmeters either look like some sort of digital tool with wires coming off of them like you've seen in the simulations, or sometimes they're this little box thing with wires coming out like this. But we represent them with a circle and a V. So we're bridging this circuit element, which in this case is a cell. Okay? So one side measures the voltage coming out of the battery. One side measures the voltage coming out. And if this circuit conserves energy like it should, V final minus V initial should equal 9 volts, since this is a 9-volt battery. Okay. All right, so I'm going to check for questions on voltage real quick before we head on to current. And it does not look like there are any questions in the Q&A or in the chat. So as a reminder, you can ask questions in the Q&A or in the chat or wherever. Oh, did I not turn on Q&A? Oops. I hit a button and it went away. Okay. This doesn't look like we have any questions. All right, so heading back, now we're going to talk about current. Okay, so you can think of current as what carries the energy from the battery to whatever device we're powering. So it's our energy carrier. Okay, so current is actually defined as the rate, okay, of charge flow. Okay. And in order for there to be a current, we need two things. Okay. We need a complete loop for the current to flow through, and we need a potential difference or a voltage. So we need some type of energy source to push that current along. Okay. So a current or a setup like this, okay, this squishy thing here is a resistor. We have a complete loop. We have an energy source. So current would be able to flow through the circuit. If we had a circuit that looked like that, well, there's no energy source in that circuit, so that wouldn't work. And if we had a circuit that looked like this, well, this circuit's open. This right here represents a switch, and right now that switch is open, and that means that there's not a complete loop, so we're not going to have any current flowing through that circuit. Okay. So, how do we calculate current? Well, current is represented with the letter I, and we calculate it by doing delta Q over T. So like I said, I is current, and we can measure current in coulombs per second, so C over S, or in ampere or amps, which is the letter A. Okay, so ampere and amps are the same thing. It's just ampere can get kind of annoying to say, so we shortened it to amps. So delta Q is the charge, or the change in charge in coulombs, which remember is represented with a letter C. And of course, T is time, and we want to measure time in seconds. Okay. So what this means is that if there's more current, there's more charge passing through a point in any given time. Okay. And we want to think of the current as being like an amount of charge passing through a given point, not necessarily the speed of the charge. So we just want to think of like a lot of charge, not necessarily the speed. Okay. So charge is another thing that must be conserved in nature. And you guys learned this through chemistry when you did reactions. So you guys know that charge is a conserved quantity. Okay. So what this means for us is there can't be any leaking charges in a circuit. Okay. So the current leaving the battery must equal the current returning to the battery. So let's simplify this a little bit, and instead of thinking about it in terms of like coulombs, let's think about it in terms of electrons. If 5 electrons leave the battery and travel through the circuit, then 5 electrons need to come back into the battery in order to conserve charge. We can't like lose an electron somewhere. That's just that doesn't happen. And this is called Kirchhoff's junction rule. And the junction rule actually states that current flowing into a point must equal current flowing out. So this Kirchhoff guy did a lot with circuits. Okay. Now, one thing that can get kind of confusing about current is the direction of the current. Okay. Now, we are all very smart human beings, and we know that electrons are the mobile charges because protons are trapped in the nucleus, which means that our charges are going to go from the negative side of the terminal and travel around the circuit, bloop, 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 like so, in what ends up being a clockwise manner based on the direction of this battery. Okay. We know that that's what's actually happening now because we know that the electrons are the mobile charge characters, is what they say. Okay. But that's not actually how we determine the direction of the current. And it's all because of Ben Franklin. Okay. So Ben Franklin, whether you know it or not, is actually one of the founding fathers, not only of our nation, but of electricity. And back in the day, we weren't able to really see the structure of an atom. So we didn't really know that electrons were the things flying around the outside. So in Ben Franklin's day, Ben was like, well, it makes the most sense that the positive charges are the ones that should be flowing. So we should be going from the positive terminal to the negative terminal. And because that has stuck around since, I don't know, the 1600s. I don't remember when Ben Franklin was alive, unfortunately. But because this has been such, trying to think of the words. Because this has been the standard for so long, even though we know that this is the correct answer, we still follow what Ben Franklin said, even though it's technically wrong. Okay. Now, will you actually need to care about the direction of current for this, what we're doing? Not really. It's just something I wanted to point out to you guys, that if you see a question and you notice that we're going from positive to negative and you're trying to think, wait, how is that possible? Electrons are attracted to positives and they're repelled from negatives. How can we go from positive to negative with electrons? We can't. Ben Franklin was wrong, but it's stuck around for so long that we still use it. Okay. But in reality of everything, it doesn't really make a difference in how we analyze the circuit. It's just something I wanted to mention. Okay. The last thing I wanted to talk about with current is what current is measured with. So current is measured with what's called an ammeter. So not an amp meter, just an ammeter. Okay. And because we actually have to have the current flow through the ammeter to measure current, these ammeters get placed in the circuit or branch that they need to measure. Okay, so voltmeters go around the element. Ammeters just get placed in the circuit. So you can kind of think of it as they need to be placed next to the element. Okay, so if I was going to measure the amount of current coming from a battery, I might have a battery and then right next to it place an ammeter. I like to think of the line and the A as being a continuation of the wire. Okay. That kind of helps me remember that my ammeters need to be placed in the circuit, not around the element like the voltmeter does. And if you look at it, the V in a voltmeter kind of looks like a bridge, so it's another easy way to remember that. Okay, so I'm going to check in for questions, and it doesn't look like there are any, which is awesome. You guys should kind of have like a basic understanding of this stuff from the like circuit stuff we did a few weeks ago, but if you do have questions, please feel free to ask. Okay, so the last little bit of information that we are going to go over today is resistance. Okay, and resistance is our energy user. So we get energy from the battery in the form of voltage. That voltage is carried through the circuit with current, and the current is then brought to the resistor where the energy is used. Okay, so resistance can take form of any electronic. So your TV is a resistor, your refrigerator, your cell phone charger, whatever. They're all considered resistors, okay, or locations of resistance. In physics, we study something called actual resistors, and they're these little ceramic usually, cylinders, okay, and they don't really do much of anything. Like, it's not like they light up or anything. Sometimes they get a little hot, okay, so they're not really like fun to look at, but the reason that we use them is because they react to current and voltage in a predictable way. Okay. Whereas, you know, your TV or other stuff like that, little bit less predictable as far as how they work in a circuit. Okay. They're also a lot easier to follow. We do occasionally use light bulbs as well, but we need them to be what's considered ohmic light bulbs, and we'll talk more about Ohm's law and what it means to be ohmic on Wednesday. Okay, but essentially we just need things that are nice and easy to follow. Okay, so we can think of resistance as opposition to charge flow. Okay, think of it as like the friction of electricity. Okay, just like friction decreases the energy of an object, resistance or resistors decrease the voltage of a charge, aka they have less energy. Okay, now we can calculate resistance of a resistor or a wire, because sometimes our wires have resistance. Now, most of the time we ignore the resistance in a wire because it's so small, but if we needed to calculate it, this is the equation we would use. So the equation is R equals this fancy Greek letter rho, which just looks like a fancy P, L over A. So again, R is the resistance, and it's measured in the Greek letter omega, but we call it an ohm. Okay, so this symbol is the Greek letter omega, but we use it to represent ohms. Okay, L, you probably know, is the length measured in meters. A is what's considered the cross-sectional area, and that's measured in meters squared. So what that means is if you were to like take a wire and cut it in half, okay, that wire is going to probably look like a circle, right? And you're taking the area of that circle, okay? And then again, this Greek letter rho here, that measures something called the resistivity, and I'll talk more about resistivity, what resistivity is in a second, and that's measured in ohms times meters, or ohm meter in parentheses. Okay, so let's talk about the area a little bit. Okay, So resistance and area, because they are on opposite sides of the fraction, right? R is proportional to 1 over A. That means that they have an inverse relationship. So what this means for us is that wider resistors or wires are, in a sense, easier to get through. Okay, which makes sense. Think about a hallway. The wider the hallway, the easier it is to get through. Okay, so the easier something is to get through, the less resistance there is. And in a circuit, what that's going to mean for us is more current flow. Right? If you had the choice between a wide hallway and a narrow hallway with the same amount of people in it, you'd probably choose the wider hallway because it's a lot easier to get through. Okay. Now, even though I mentioned this before, the area can be any shape. Any shape, right? Like we could have a circular cross-sectional area, and in that case, we would calculate that by doing pi r squared. Or we could have a strange like rectangular wire, and in that case, it would be base times height. We could have a triangular wire or anything like that too. Most commonly, though, we're dealing with circular wires or resistors, sometimes square. Okay. All right, let's talk about resistivity a little bit more. Okay, so looking at the equation, R is directly proportional to resistivity, which means if I was to graph resistivity versus R, I would get a nice direct relationship. Okay. Now you might be thinking, what the heck is this resistivity thing? Well, resistivity is a measure of conductance. So how well electrons can travel through a given material. So something with a high resistivity would be a conductor, like metal, and something with low resistivity would be an insulator, like plastic. Insulator. Okay. Now, a few things about resistivity. Resistivity is material. So, you know, whether it's metal or plastic, and temperature dependent. Okay. Now, what ends up happening is as the temperature increases, resistivity increases, so resistance increases. So one thing to watch out for is a lot of students, when reading questions, they'll accidentally confuse resistivity with resistance. Yes, they look very similar, but they are different things. So make sure when you're reading questions, you're actually solving for the thing it's asking for. Now, you might be thinking, why does temperature affect the resistivity and therefore the resistance? Well, if you think back to last year in chemistry, you might remember that something interesting happens when you heat up the molecules of a substance. Okay? When you heat up molecules of a substance, the molecules move more, right? So hotter molecules move more. Okay? So let's say here's a resistor, and it's made of some type of semiconductor material, right? If this resistor is relatively cold, right? Here are the molecules of whatever substance this resistor is made out of. If the resistor is cold, these molecules are relatively stationary, which means the electron flowing through them can find a relatively nice, easy path to get through. However, if we have that same wire, okay, and that wire is hot, that's not how you spell hot, only one T. Those same molecules are not going to be at rest. Instead, they're going to probably be bouncing all over the place, okay? Which means that the electron is now going to have a much harder time getting through, because in order to travel through, it has to, in a sense, make its way through all of these molecules. So it's going to probably bump into some and have a much more difficult path getting through. Okay. So you can think of this in the same hallway example, right? Let's say that each of these molecules represent a person and you are the electron, right? In a cold hallway, so to speak, let's say all of the people are standing still. Much easier for you to get through. You just pick a line and you go. In a hot hallway, let's say all these people are just like running around in random formats. Definitely going to be much harder for you, the electron, to get through, because you're not going to be able to pick one path and stay on it. You're going to have to constantly be changing your path. You might run into people, right? So that's why temperature can affect the resistivity and therefore the resistance of a specific material, okay? And on Wednesday, we'll also talk about how this can cause light bulbs to burn out when you first turn them on. Okay, and why they really only burn out when you first turn them on and not when they've been on for a while. All right, I'm just checking through my notes and making sure that I talked about everything that I did or wanted to, and it's looking like I did. So I'm going to come back to the video and see if you guys have any questions. Oops. And it does not look like there are any questions. Okay. So I think that means we are going to end this live and end these notes. The notes for Wednesday are going to be on Ohm's law and power, and those are going to be at 11, because I know a lot of teachers are live at this 1 p.m. time, so I want to make sure as many people can come as want to. So that is it for these notes, and I will see you guys soon. Bye.